Okay, picture this for a second. You're facing a solid brick wall, right? No door, no tools, nothing. But what if somehow you could just find yourself on the other side? Not, breaking through, but just suddenly being there. Seems impossible, doesn't it? Pure fantasy stuff.
Right. It sounds completely nuts from our everyday perspective.
Yeah.
But down at the quantum level, something very much like that is, well, it's fundamental. We're talking about quantum tunneling.
Yeah.
It's this process where particles manage to get through barriers, even when they, classically speaking, absolutely shouldn't have the energy to.
And that's exactly what we're trying to, get our heads around today in this deep dive. We've been digging into these excerpts from a source called Quantum Tunneling, Impossible Made Real. Our mission really is to unpack this genuinely weird but essential piece of how the universe works that these sources describe.
Yeah, and what's so striking, what these sources really highlight, is how much it messes with our intuition. Like rolling a ball up a hill. If it's not fast enough, doesn't have the energy, it just rolls back down. Simple, can't get over. That's classical physics for you.
But quantum particles aren't just little balls, are they? That's the key thing this material keeps coming back to, their wave nature.
Exactly. Particles, electrons, protons, you name it, they act like waves too.
Yeah.
And waves aren't located in just one spot. They're spread out. There's a probability associated with them.
A probability landscape, yeah. Described by math, the wave function.
Right. And the insight from these readings is that this wave, this probability wave, it doesn't just slam into a barrier like our wall and stop if the energy is too low. Instead, part of that wave, the amplitude, which tells you the chance of finding the particle, it actually extends into the barrier.
Okay, wait, so the chance of finding it sort of leaks into the wall?
Precisely. I mean, it drops off fast, exponentially as it goes deeper.
Yeah.
But, and this is the crucial bit, if the barrier isn't infinitely thick or impossibly high, that fading wave can still have a little bit of amplitude, a non-zero probability on the other side.
So there's a real actual chance, maybe small, but real, that the particle that was definitely on one side can just be detected on the other side without having, climbed over. It just appears there.
That's tunneling. It bypasses the energy requirement through this quantum weirdness, this probabilistic nature.
Okay, that's pretty mind-bending.
And it's not just some theoretical curiosity. The sources are really clear on this. It's happening all the time, and it's vital. Think about the sun.
Right, the fusion thing. That's where this gets, huge. Inside the sun, you've got hydrogen nuclei, protons, basically. They need to fuse to make helium release energy, but they're both positively charged, so they push each other away. A lot.
A huge amount. And even though it's incredibly hot and dense in the sun's core, they still don't typically have enough raw thermal energy to just smash through that repulsion, that energy barrier. Classically, they shouldn't fuse often enough.
But they do, because of tunneling.
Exactly. Quantum tunneling gives a fraction of them a way to sort of cheat. They can probabilistically bypass that repulsive barrier just for an instant, getting close enough for the strong nuclear force, which only works at tiny distances but is super powerful, to grab hold and fuse them.
Wow. So no tunneling, no sunshine, basically.
Pretty much. The sun wouldn't burn the way it does. Life on Earth depends on this quantum effect constantly happening. That's a key takeaway from the source material.
That is, yeah, that's profound. And it's not just stars, right? Sources mentioned technology, too.
Oh, yeah. Scanning tunneling microscopes, STMs, incredible devices. They let us see individual atoms. They work by bringing this incredibly sharp metal tip really, really close to a surface. Close, but not touching. There's a tiny gap, an energy barrier.
And electrons tunnel across that tiny gap, from the surface to the tip, or vice versa.
That's it. They don't have the energy to classically jump it, but their wave function leaks across. They tunnel. And by measuring how much current tunnels as you scan the tip, you build up a map of the surface, atom by atom. Amazing.
And semiconductors too, right? Our electronics.
Definitely. As transistors and things get smaller and smaller, down to the nanometer scale, the barriers get thinner. So electrons can start tunneling through parts they're classically supposed to be blocked by. Sometimes it's a problem, leakage, Other times, engineers actually design devices using tunneling.
So this deep dive, based on quantum tunneling, impossible made real, really shows us a universe that doesn't play by our everyday rules.
Yeah, it tells us energy barriers aren't always insurmountable walls. Sometimes probability just lets you be on the other side.
It really messes with our ideas of cause and effect, doesn't it? The impossible, or at least the incredibly improbable, becomes possible at these scales.
It reveals a reality that's much more flexible, I guess, more surprising than our intuition suggests. It's fundamental to how stars work. how we explore the nanoscale.
So wrapping up, the core idea is particles acting like waves lets them sneak through barriers. It powers the sun, enables tech like STMs, it challenges our whole sense of reality.
Absolutely. And these sources kind of leave us hanging with a really interesting thought, don't they?
Yeah, that final provocative question. If reality down at the quantum level lets the improbable happen, lets particles bypass these impossible-seeming barriers,
Mhm.
what else about the universe might be way stranger, way more counterintuitive than we currently even guess?
Hmm. Something to think about for sure. The universe might be weirder than we can imagine.